Alright, 5 more problems to finish assignment 10. The first one is we're going to use Ampere's law to solve for the field inside a coil. Then we're going to use Ampere's law to solve for the magnetic field inside and outside a long wire. Then we're going to use the Biot-Savart law to solve for the current due to a circular loop. Then we're going to use the Biot-Savart law to solve for the current through a circular loop along the axis of the loop. That's like the Helmholtz coils. And then we're going to use the Biot-Savart law to solve for the current due to a wire segment, a short wire segment. And those are the 5 problems. So let's start with the coil, and that's number 13. And so you see we've cut the coil in half, and Ampere's law, here it is, says that if you integrate around a closed loop, if you integrate B dot ds, which is B ds times the cosine of the angle between them, it will be equal to mu naught times the current enclosed. And you might not just guess this from scratch, but it turns out that this problem is readily solved if we choose a closed loop which is rectangular. And there it is. So we're going to integrate first from a to b. We're going to do this integral from a to b. And if we notice that b everywhere along this wire is pointing in the same direction. So if I draw any ds on this segment from A to B, any ds is going to be in this direction, and it's going to be parallel to the field. So the cosine of 0 is 1. And whatever the magnetic field is here, we don't know what it is, but whatever it is, it's constant. So since it's constant, it can come out of the integral. And all we got to do between A and B is integrate all the ds's. And if we take every ds from A to B, then that's just the length L. So this side of the equation simply becomes B times L, and that's going to be equal to mu naught times the current enclosed in the loop. Well, we have to finish the rest of the integral. But notice, once we turn the corner and go this way, the ds's are pointing up and the magnetic field is pointing to the left. And so they're perpendicular to each other. And when you do the dot product, vectors that are perpendicular, the cosine of 90 is 0. So the integral all along here is 0. Once you get outside the coil, the field becomes so weak that we can consider the field to be 0. So when you integrate here, here, and back to here, it's all 0. And then this piece, this short piece, which is perpendicular to the field, is 0. So of the 4 sides of the square, 3 of them end up being 0. And so this is the answer. But we have to know how much current is enclosed because there's not just one wire in there. So the number of current, so B times L equals mu naught times the current enclosed. Well, the current enclosed is just going to be whatever the current is in the wire times the number of wires that are in there. So we simply multiply the number of wires times the current, and then we have our result. And so if we divide by L, B equals mu naught N over L times I. And the N over L, whatever number of windings there are in this distance L, is the winding density. So we often write this as B equals mu naught little n, which is the winding density, or the N over L times I. So there it is. There's our equation for the field inside a coil, derived quite quickly using Ampere's law. So in problem 14, we use Ampere's law again to find the field outside and inside a current carrying wire. So let's do it for the outside first. And it's better to use this figure. So now I made the wire smaller because we're outside it. And so since the figure uses dl for the small displacement vector, we'll just write Ampere's law as the integral around the closed loop of b dot dl. That's just the same purpose as the ds was. It's just choice of a letter, and mu naught I enclosed. And so what we're doing is we're doing the integral of b times dl times the cosine of the angle between them equals mu naught I. Now notice, since so we're going to draw a loop which is a circle. We can choose whatever loop we want. And in the last problem, the rectangle matched the symmetry of the problem. But in this case, it makes sense to draw a circle, because that means whatever dl or ds I draw along the circle, the b is going to be parallel to it. So if I pick a dl here, the b is parallel to it. If I pick a dl here, the field is parallel to it. And so the cosine of theta is always 1. That's why we choose a circular path. And since it's a circle, it's the same distance from the wire, whatever the field is, even though we don't yet know what it is, it's going to be constant. So like we did earlier, it comes out of the integral. And so we have b times the integral around the closed loop of all the dl's times 1 equals mu naught I enclosed. And so if we go around a circle, closed loop, and add up all the displacement vectors, we get the circumference of the circle. So the integral becomes 2 pi r, and that's equal to mu naught times the current enclosed, which is the current in the wire. And then when I divide that out, I end up with b equals mu naught I over 2 pi r. That's the result that we've been familiar with. Sometimes we call it A, or sometimes I call it S, right? But it's always the distance from the wire to the point where we're calculating the field. All right, now we'll go inside the wire. So I made a big wire, magnified it, and inside, current is coming out of the page towards us, and it's evenly distributed over the entire wire. So this is a cross section of the wire, and we're looking down the wire, and it's circular. So our Amperian loop should be circular. So say we wanted to know, oh, what's the field inside a wire, say about halfway toward the center. So we would just draw a circle centered on the center of the wire, which has, well, since the wire radius, if we call the wire radius r, let's just call this distance a. Could be r over 2 or anything. So we want to find the field at a point A, a distance a from the center of the wire, where a is smaller than the radius of the wire. So the field inside the wire, it's going to have the same symmetry as the last problem. If I take a dl or a ds along the wire, the field is going to be, whatever it is, it's going to be the same along the wire, and by right-hand rule number 2, it has to be in the same direction as the dl. So we end up getting the same integral, we get b is constant. The adding up all the ds's or dl's, we get the circumference of the circle, which in this case is 2 pi a. That's the circumference of that green loop inside the wire. And so that has to be equal to mu naught times I enclosed. But the amount of I enclosed is not all the I, right? Whatever the I is, it's going to be some fraction of the I. So what fraction? If I'm halfway in, is it going to be half the current? The answer is no. It's a fraction of the cross-section areas. So the I, if we take pi a squared, that's the area of this part, and we compare it to the area of the whole thing, that would be pi r squared, right? Turns out if you're only halfway out, the area is 1/4 the area, so you only have 1/4 the current. So anyway, the pi's cancel, and the ratio is a over r, a squared over r squared. And then when I divide by 2 pi a, I get b equals mu naught I. Notice that that a actually cancels one of those. Mu naught I over 2 pi r squared times a. That's the result. And so r squared, r is a constant. It's the radius of the wire. But you see, as a gets smaller, b gets smaller. And if a goes to 0, b goes to 0, which makes sense because over at the center of the wire, the field should be 0 at the center. And as we go out, the field gets bigger. And when if a equals r, then the result becomes mu naught I r over 2 pi r squared, so one of the r's cancels, and you have mu naught I over 2 pi r. That's good. That gives us back the same result that we know for the current outside a wire at the surface of the wire. There's one more problem that can be solved using Ampere's law, and that's this circular coil, this donut or torus or toroid coil, where the coil closes on itself and all the field is inside the coil. So this is a problem that lends itself to Ampere's law, but it's not part of the assignment, so we won't do it. We'll move on to problem 15, which is finding the field at the center of a current loop. And for that we'll use the Biot-Savart law. So here's a current loop, and we want to know the field at the center. And by right-hand rule number 3, we know the direction of the field is out of the page. But what's the strength of the field? So we integrate around the wire, and they use dl instead of ds, so I'm using dl. And at every point along the wire, we do dl cross I hat. So you see dl in this spot is in this direction, and the r hat points toward the center, so they're perpendicular, right? The dl cross r hat is dl times r hat, which is 1 unit vector, times the sine of the angle, and if the sine of the angle here is 90 degrees, that's 1. Now if we take a dl here, the r hat points toward the center, it's still perpendicular. And if we take a dl down here, the r hat points toward the center and is perpendicular. So you see every dl along the circle, since we're finding the field at the center of the circle, is going to be perpendicular. And the current is the same. And the distance, this r is the distance from the wire segment, the dl, to the point. And for every dl, that distance is the radius of the circle. So everything inside the integral is a constant. And so we get b, the mu naught comes out, the I comes out. 4 pi are constants, obviously. And in this case, for this example, the r squared is a constant. So all we're doing is we're integrating all the dl's. And what is that? That's the circumference of a circle. So the integral of all the dl's is 2 pi r. So that leaves that 2. The pi's cancel. One of the r's cancel one of these r's. And you see the only thing that's left over, this is the equation on your equation sheet, is mu naught I over 2r. And then we might think about, does that make sense? Yeah, more I will mean a stronger field, and a bigger R would mean a weaker field, and a smaller r would mean a stronger field, because that puts the wire, the source of the field, closer to the point where we're calculating the field. Good, so that's that problem. So for problem 16, we want to take the current loop and find the field away from the center along an axis through the center. And we're going to use both of these figures to do that. They give us different perspectives, different angles. So in you can see these more clearly in Moodle, but this is called figure 1 and this is called figure 2, and there are some differences that you need to notice. So in this figure, this is the x-axis and this is the y-axis, and this is the z-axis. It's a little bit easier to see if you look at Moodle rather than the screen here. And in this one, so this distance from the center to this point, and this one is going to be called y. It's not labeled. And in this one, in figure 2, the distance from the center to the point is called z. And that's why there's a z here, because the distance from any place on the ring to the point, so if you take a dl here and you're calculating the field here, the relevant distance is this r. And that r, they use a little r in both figures, but in this, the r is the square root of, the square root of z over the radius of the circle. So if you take the radius squared and the z squared, you get r. So if you take the square root of z squared plus r squared, you get this little r. And this is also, in this figure, it's also called little r, but it's going to be the radius r squared plus y squared square root will be this distance r, right? Because this is a right triangle. And the angles are also labeled differently. In this angle, theta is the angle between here and here, and theta is the angle of the magnetic field vector. Okay, I'm getting a little bit ahead of myself, so let's start with this figure and see if we can understand where these magnetic field vectors come from. So in this case, I'm going to use the differential form that for every dl cross r hat times this, you're going to get a dB. So if we take a dl here and an r hat here, it's a little hard to visualize, but these are perpendicular to each other. Even though this is going down, the angle between the dl and the r hat is 90 degrees, so that's the sine of 90, which is 1. And the r, in this case, the r is what? It's the r, big R, capital R squared, plus y squared. And for this one, this distance r is going to be r squared plus c squared. And that's why when we write this down, it shows you that r squared equals c squared plus r squared. But notice that when you do dl cross r, the direction of the field vector for this dl is in this direction. It has to be perpendicular to this line. And so I'm not going to go through the geometry, but if we choose this angle theta here, and this is perpendicular to this, then this is 90 minus theta. This has to be 90. This angle, those two angles are going to be equal. And it makes sense because this figure chooses this angle for the theta, and so the theta ends up here, not here. And the reason we need to know this angle is, watch, this vector goes up like this. If we take a dl here, then when we do dl cross r hat, this is a little bit crazy to visualize. So here's the r, and so my fingers are coming out, my index finger's coming out, my other fingers are pointing down along here, and my thumb will point up in this direction. And since this is theta, this is 90 minus theta, that's theta, this is 90 minus theta. So this vector, it's easier to picture here, has a y component. Actually, it's an x component in this figure, and a z component this way, because this is called the z-axis. And so if we did all the dl's around here, what you would get is you would get a series of dBs, a series of magnetic field vectors that would sweep out a cone. And so all the, in this case, all the x components and y components would cancel in pairs, and the final field in this figure is going to be along z, and in this field it's going to be along y. So let's find, this is the dB, but what we want is the thing that we need to integrate are all the dy's. So we have to take the cosine of theta. And the cosine of theta, this angle, is the adjacent over the hypotenuse. So we've got to multiply this by the cosine of theta, which is the adjacent, the r over this. So let me write that down and see if we can follow it. Okay, so here we go. So this dl gives us a dB, a magnetic field vector, and all we want is the y component. Remember, this is our y-axis. All we want is the y component of it. And if this is our angle theta, then the y component will be the dB times the cosine of theta. So the dB is this, where the r squared is this. So we have mu naught I dl 4 pi r squared, which is r squared plus y squared. And then the cosine of theta is the adjacent r over the hypotenuse r squared plus y squared square root. So this is r squared plus y squared to the 1/2 power, and that's how you get the 3/2 power. Okay, now we have to add up all the dy's. We have to integrate all these dby's to get the final result along the y-axis, which is the field due to this coil. And notice that the mu naught I, everything in this integral is a constant except for the dl. The I doesn't vary, the 4 pi doesn't vary. This is the radius of the circle, this is the distance to the point, that's not varying. The angle between the dl and the r hat, we said, is always 90 degrees, so that just becomes 1. And so all we got to do is integrate this, and that's the integral, just like we did last time, of all the dl's around the circle is 2 pi r. So if we bring that up here, we're going to have that by, the total by after we do the integration, is mu naught I. The integral of the dl is 2 pi r, the radius of the circle. Then we have another r, this r. And then we have 4 pi. And then we have r squared plus y squared to the 3/2 power. Right, because the square root is there. And so the 2 pi, we'll just leave this as 2. And so this finally ends up being, if we clean it up a little bit, it's going to be the total field along the y-axis is going to be mu naught I r squared over 2 r squared plus y squared to the 3/2 power. It's a little bit hard to read, but that is the result. Okay, I cleaned it up and wrote the result down. Now watch what happens if we let's take this back. If we let this distance y go to 0, that puts us back at the center. So watch what happens if we let y equal 0. If we take this and let y equal 0, try it. You're going to have mu naught I r squared over 2, let y be equal to 0, you have r squared to the 3/2 power, so that's equal to r cubed, and so you have r squared over r squared divided by r cubed, you end up with mu naught I over 2r. That's a good sign. That's the same result we got last time for the field at the center of a coil, and this gives us the same result. So that's a good indication that this is correct. So final problem 17 here. We know what the field is due to a long straight wire, but what if we have a short piece of wire? and we're relatively far away from it, and we want to find the field. So we draw this figure, put down the point, and then we have to integrate all the, we use the Biot-Savart law, which says take any ds, in this case it's a dx because this is the x-axis, and cross it with r hat and multiply it by mu naught times the current in the wire, and divide it by 4 pi times the distance from the dx to the point. And that distance in this figure is marked as r. So if I take the Biot-Savart law and I write it for this particular problem, I'm going to have mu naught I, and the ds cross r hat is dx times r hat, which is 1, so I'm not going to write it down, times the sine of the angle, that's theta, the angle between the r hat. So we have sine theta, and that's over 4 pi times this distance squared, which is r squared. And then if you look at the solution they do a trig substitution so that it's integrated over an angle. But if you look at textbooks or you look on the internet, we can also write this r in terms of x. This r, right, would be x squared plus r squared if you look at the figure. And then we could write the sine of theta in terms of x, and we could do this integration in x rather than in theta. But the solution they show is in theta, and that gives you the result of this problem, integrating from theta 1, from any theta 1 to theta 2. And so it gives you a way of calculating the electric field for a point at any distance of a wire of any length.